Hello, ATS EVS 533 students. Dr. Shragi here, and I appreciate your patience with everything this week. And we're going to do an online lecture real quick here that is going to be a review for the upcoming exam 2. Obviously, of course, any of the stuff that you have questions about, just get a hold of me and we'll get it all sorted out. Now, if you remember at the beginning of the second module, I pointed you to, I think it was about 4 lectures that we labeled like a 100 level background. Everybody in this class has a very different background in terms of what classes they've had in physics and so on. And I just wanted to make sure, without spending a huge amount of time with the whole class on about things like, do you know the very basics of radiative transfer and so on, or words like joules and watts per square meter, and terms like electromagnetic spectrum or shortwave or solar or terrestrial or long wave or whatever. And so, if you go back on Blue Line to that set of lectures there, you'll see that there was, I think I said it's like 4 different lectures there. Let me just repeat some of the verbiage I had on those slides. It said, we're going to be using terms like energy and power. We're going to be talking about the transfer of energy in terms of conduction, convection, advection, and radiation, with obviously radiation being the most important in this module of the course. We're going to be talking about different parts of the electromagnetic spectrum. That was, when we talk about different wavelengths and so on. We were talking about the radiation as being long wave or short wave or solar or terrestrial. We talked about radiation in terms of the 2 main radiation laws, namely Wien's law and Stefan-Boltzmann's law. You really do need to know that stuff. My guess is for 90% of you guys, this is fine and you have it under control. But if there's ideas about this that you don't understand, please do let me know. In the same way, I believe there was another one where I had this verbiage. I said, we're going to be needing to be able to describe the interaction between matter and radiation in terms of emission, absorption, transmission, and reflection of radiation. All of that stuff we're going to be able to do for the entire part of the visible spectrum, for example, albedo, as well as the monochromatic absorptivity, transmissivity, and monochromatic reflectivity. Make sure you know what that word monochromatic means. Again, you certainly can talk to me about that kind of stuff, or you can review that lecture from a 100 level class if some of those concepts are something that you don't understand. Another lecture that we had was more about the energy balance. Now, we did the energy balance in more detail in this 500 level version of the course, but if, some of these basic ideas of building a radiation balance and how that results in temperature changes and so on, if some of that stuff was confusing to you, be sure you do review that lecture on the 100 level background page that talks about a discussion of climate requiring us to understand the energy balance of the Earth. Energy balance about conservation of energy and maintaining thermal equilibrium. You remember, we've seen these words other places in this module. You'll need to understand about all the things that can happen to incoming solar radiation, like reflection by clouds and aerosols, or reflection by the surface of the Earth. That could also include things like absorption by gases or reflection by, you'll need to understand all about things that can happen to outgoing long-wave radiation, including transmission of that radiation through the atmospheric window and absorption of that radiation by greenhouse gases, and so on. Again, if those concepts are unclear, this is a good time to either get your questions answered or go back and watch that 100 level lecture, and make sure that you do understand those concepts. And then I believe the fourth one that I pointed to you at that time was labeled that we are going to be using this information to discuss climate change. We're going to be needing to know about the ways in which human activity alters the energy balance of the Earth. We need to know what greenhouse gases are and about how they're selective absorbers and how they partially close the atmospheric window and so on. If those are concepts that you're comfortable with after seeing the rest of the module, great. If you need that level of background, obviously, please go get it or let me know or whatever. All right, we had 6 days then of material in this module that was just sort of an overview of some of the physics of the radiation in the Earth's atmosphere. And the first day here, I'm going to just be showing you some screen captures of slides here with a little bit of fresh verbiage over here. If you flip through that lecture that we had from the first day and look back on it, what should be really clear is that we were heading all of this way. We weren't ready yet to use the word radiative forcing, but that's really where we were going. We're just sort of starting to frame the idea in terms of like energy in and energy out. We first did it with like a warm pan that we put into the refrigerator, which was giving off a certain amount of radiation. That was its energy out, but it was receiving a certain amount of radiation from the other objects in the refrigerator. That was energy in. And we were starting to get this idea that there would be a change in temperature, or which is related to a change in internal energy, due to this imbalance between energy in and energy out. We weren't ready for ideas like radiative forcing, but that's where we were headed with this. And given some kind of energy imbalance, the radiative forcing was going to try to drive the system towards some new kinds of thermal equilibrium, where the same amount of energy was going in as coming out. Now, of course, the kinds of questions that this leads to later in the module are stuff like, how long was this going to take, and how big of the temperature change going to be? We weren't ready for words like climate sensitivity parameter and so on, but that's where we were really headed with all of this stuff. And then we had a whole string of slides that first day that was about picking apart the Earth's energy balance. And we were basing it on this slide that is kind of a classic thing that comes from NASA, where it has the actual global measurements. This is based on measurements like from satellites and so on, of the fluxes of shortwave radiation and long-wave radiation and so on. You do need to know, like, for example, what all these units are and so on, but memorizing the numbers is not in any way important for this. But understanding all these processes that are at work here in this slide, what is the stuff that I have highlighted in red there? I think that's reflected off of the surface of the Earth or reflected off of clouds. Is that what is that role is that playing in the Earth's energy budget? For example, here's a particularly good example. Here I'm highlighting the long wave radiation that's coming down from the sky. This is, would be long wave down. It is radiation that's being emitted by clouds and gases in the atmosphere. It is back radiation, to use another term that we saw. And remember that in the end, it turned out that according to the observations, there is a net energy imbalance at the surface of the Earth, and it's about 0.6 watts per square meter. That is a number, of course, that comes back to haunt us like all the way later in like the 6th lecture of this course. But when you actually do the radiative balance of all the sources and sinks of heat, what are the energy in and energy out of the surface of the Earth, it works out to a little more than a half a watt per square meter. And then we could sort of play with this little conceptual model that we have here of the energy balance of the Earth, and we can start saying things like, well, what would happen if we had the same energy balance, but we would say that the greenhouse gases aren't doing this. We had an atmosphere in which we had a hypothetical energy balance in which the greenhouse gases in the atmosphere did not absorb or emit long-wave radiation. An interesting challenge, and when you actually pick through this all here and so on, you end up with a planet that has a temperature far, far lower than what is observed. In order to make the energy balance be as close to balance as it is at the present time, the temperature of a planet without greenhouse gases would end up being about 178 K, which is about 140 degrees below 0 Fahrenheit. So just putting this into context with what we saw later in the module, this means that there's going to be some new equilibrium temperature, and that new temperature is this very low number. This is, with the radiative forcings that would exist in an atmosphere without the greenhouse gases, this is the temperature the surface of the Earth would need to be in order to emit the right amount of long-wave radiation to keep the Earth in energy balance. Well, if that's apparently going to be the case, then clearly we need some very clear understanding as to what's going on. What are these greenhouse gases actually doing in the Earth's atmosphere? And in order to kind of pick this apart, what we did is we made a diagram where I stretched the scales of two different plots from two different books so that they overlapped and matched up. And we built this diagram here where the top panel was how much radiation the surface emits at, as it happens to be, 300 K. If the surface of the Earth were 300 Kelvin, this is how much radiation would be emitted at each of these wavelengths. The surface of the Earth is a little bit cooler than 300, but that's a good estimate to be working with. And then you have on that other diagram there, the kind of lower one, that is the transmissivity of the Earth's atmosphere at each of those wavelengths, the monochromatic transmissivity. And then we started identifying different bands on the electromagnetic spectrum, and we started seeing that they had very different properties. For example, highlighted in light blue there, we had one range of wavelengths that the Earth emits a great deal of, and by and large, the atmosphere transmits. The monochromatic transmissivity of the atmosphere at those wavelengths was very high. This was the phenomenon, of course, known as the atmospheric window. It's that range of wavelengths of radiation that is effectively emitted by the surface of the Earth, but is in general transmitted by the atmosphere, which you don't generally expect from long-wave radiation. You usually expect the long-wave radiation to be absorbed by the atmosphere, but not in those range of wavelengths. Um, all along, be trying to tie it to other ideas that we learned later in the module. For example, what is the monochromatic optical depth of the atmosphere at wavelengths associated with the atmospheric window? Well, remember, optical depth is about how much that layer of the atmosphere resists the flow of radiation at that wavelength. Well, clearly in the atmospheric window, the monochromatic optical depth is very small. Those layers don't in general resist the flow of radiation in those wavelengths. In contrast, we also identified two other bands of radiation where the Earth emits a fair amount of radiation in those wavelengths. And if you actually look at the second panel that shows the transmissivity of the Earth's atmosphere at those wavelengths, well, it doesn't, even with the existing concentrations of greenhouse gases in the Earth's atmosphere, practically nothing of that radiation is transmitted through the Earth's atmosphere. You could ask yourself things like, what is the monochromatic optical depth of the atmosphere for these wavelengths? Well, again, just to tie it to ideas that are later in the lecture where we started talking about optical depth, if optical depth is a measure of how much that layer resists the flow of radiation at that wavelength, clearly the optical depth of this layer for those wavelengths is going to be very high. It doesn't range from 0 to 1, it goes from 0 to infinite. So you would have a very large optical depth for the atmosphere at these wavelengths. Notice that already with the existing concentrations of greenhouse gases in the Earth's atmosphere, we already basically don't transmit any radiation in those wavelengths. So increasing greenhouse gases actually makes no difference at 6 microns or 14 microns or something like that, because at those wavelengths, there's already no transmission of radiation to space. The atmosphere is completely opaque at those wavelengths. In contrast, of course, there was one other set we looked at of these three different ranges of these different ranges of wavelengths, these bands. And those, again, were three different ranges of wavelengths that actually the atmosphere emits a fair amount, the surface of the Earth emits a fair amount of. And in this case, the transmissivity of the Earth's atmosphere is not 0, but not 100 either. Somewhere, averaged around 50% or something like that. For this radiation, the monochromatic optical depth of the atmosphere is somewhat moderate, maybe a value of 1 or 1.5 or something like that. We'll see more about optical depth in a little bit, but, it has a transmissivity of about 0.5. Notice, though, it's going to be very keenly dependent on the concentration of the greenhouse gases. If we increase the amount of greenhouse gases, the transmissivity of the atmosphere for this long-wave radiation in these three bands is going to drop and drop and drop until eventually these bands are absorbing radiation rather than transmitting it. There's a big consequence, obviously, for global warming then in these three bands based on the concentration of greenhouse gases. If we actually then transfer those three bands over to another plot, what we saw is it is the greenhouse gases that are the ones that are absorbing in those three bands of the electromagnetic spectrum. It's things like water vapor and methane and carbon dioxide and nitrous oxide and so on. And these greenhouse gases, man, in a class like physical climatology, you really need to know then what these greenhouse gases are doing. You need to know their names. You need to know how they're absorbing long-wave radiation. They emit long-wave radiation both up and down, and how increasing their concentration increases the greenhouse effect and so on. And then we decided to get quantitative about it. We decided to actually that day pick this apart and say, let's actually see if we can use our quantitative understanding of radiative transfer in the atmosphere to build a very simple one-layer model, just a very simple little quantitative conceptual model here that is going to explain the flow of radiation through the Earth's atmosphere. And we originally started with just a one-layer model. We're approximating there's a surface of the Earth, and then there's one layer of the atmosphere that either absorbs radiation or transmits it or whatever at any given wavelength. And we made a whole bunch of assumptions to get to this point, but we were able to come up with an energy model here through this one-layer model. We made some approximations or some assumptions here. You might remember, for example, we assumed that the layer was completely transparent to shortwave radiation. We assumed that the layer was completely opaque to long-wave radiation. The layer itself of the atmosphere would be of a temperature that it was emitting long-wave radiation, not short-wave radiation. The atmosphere is not going to be as hot as the surface of the sun, for example. And so we have this diagram here that we put together where the red 238 down is long-wave radiation. The atmosphere is emitting down towards the surface of the Earth. The 238 down that is the blue arrow that's pointing down, that is shortwave radiation making it through our one-layer atmosphere to the surface of the Earth. To maintain energy balance, we have to maintain 476 watts per square meter upward in form of long-wave radiation emitted by the surface of the Earth. And you can pick this thing apart and figure out what each of those different arrows on there was. One thing as I was putting this slide together occurred to me, I don't even see an atmospheric window on this diagram. There doesn't seem to be any long-wave radiation that is emitted by the surface, but that radiation itself makes it out. That black arrow, it doesn't go all the way up to outer space, out through the first layer. Why? What assumption did we make that got rid of that? Well, when you actually picked this thing apart and put numbers in there for, if we're going to have to emit 476 watts per square meter at the surface, then in order to do that, we're going to have to use Stefan-Boltzmann's law, and we figure out what is the temperature of the Earth that will make that happen. And you get 303 Kelvin, which is 86 Fahrenheit, which does not sound so bad. That actually does not sound terribly far away from the correct answer as to what is the temperature of the planet of the Earth. And it's a whole lot warmer than the planet would have been in our little energy balance that we did before without greenhouse gases in the Earth's atmosphere. But it turns out to basically be a coincidence. The answer here is we made some pretty gross assumptions, like the atmosphere is completely transparent to shortwave radiation. It's completely opaque to longwave. We know those things aren't true. It's just our answers kind of canceled each other. And it wasn't really until the second day in the course that we started picking this thing apart and saying, let's see if we can do better. Let's come up with a two-layer model that has certain assumptions behind it. Like we took each of these layers. Each of these layers was completely transparent to shortwave radiation. Each of these layers was completely opaque to longwave radiation, etc. And we said, let's try to set up a energy balance here for a simple two-layer model here. And again, you can start picking through it. I have some suggestions of questions you can try to answer for yourself here on this slide. And, okay, well, what is the black arrow with 714 watts per square meter up from the surface? What is the red arrow with 238 watts per square meter going up, etc.? You can ask yourself all those questions and see if you can figure out, is that what's emitting that radiation? What's transmitting it? Is it long wave? Is it short wave? Is it headed up? Is it headed down, etc.? Once again, by the way, just to kind of relate this to something you saw already, where is the atmospheric window in this diagram? It's not there. Why? What assumption did we make that got rid of the atmospheric window on this diagram here? And what you do is you plug in the math, you figure out, okay, when I actually worked through this energy two-layer model here, I got that the surface of the Earth would have to be emitting 714 watts per square meter in order to be in energy balance. And then you plug that emission, 714 watts per square meter, into Stefan-Boltzmann law, and you get that the temperature of the Earth has to be 335 Kelvin, which is 144 Fahrenheit. Oh my, we're not too happy with that, right? This is an even warmer planet than what we got with a one-layer model. The one-layer model is actually a whole lot closer, almost suspiciously close. But that was largely just big errors canceling each other out. What was going wrong here? Well, we had terrible assumptions, actually, that were getting worse the more layers we added. In particular, this assumption that every layer of the atmosphere had to be completely opaque to long-wave radiation. Effectively, we were just laying more and more heavy blankets on top of the surface of the Earth, where each one was completely opaque to long-wave radiation. Each one of them had effectively an almost infinite optical depth at long wave radiation. This just was not. We were making all kinds of mistakes here. This was not the right way to solve this problem. So we tried a more realistic model. We said, okay, instead, let's say that the transmissivity of each of these layers was 90% for shortwave radiation, and the transmissivity of each of these layers for long-wave radiation was 10%. And we built this rather nice-looking two-layer model of the atmosphere here with lots of fluxes of radiation. Hey, we have an atmospheric window now where that radiation that is emitted by the surface of the Earth, xg, it's that black arrow. Notice that some of it actually does get all the way through the Earth's atmosphere, and it looks like about 1% of it does get through the Earth's atmosphere. That's interesting. We now have an atmospheric window. 1% does not sound anywhere realistic. We'd have to go back to our observations on that slide from NASA. But we are at least in the ballpark. We're starting to get some processes that look pretty realistic here. And there I wrote on here some examples of the kinds of questions I could pick off of this thing. Like, for example, E is the amount of radiation incident upon the top of the Earth's atmosphere from the sun. at the surface, what's encountering the surface is only 0.81 E. Why? What happened to the other 0.19 E? Where did that go? Those are good questions to be figuring out. Now, I would never expect you to actually be able to put together this system of 3 equations and 3 unknowns that then is how you actually solve to find what is the amount of radiation being emitted by the surface and by each of the 2 layers and so on. That's what high school algebra was for. At some point in your high school algebra term, you got this all sorted out, and it's not that important here. It isn't even, I'm not even going to ask you on the test to like actually set up a set of equations like this, but it would be fair for me to ask you, what are these equations? Well, each of them represents the energy balance at some particular place in the Earth atmosphere system. Well, like like at the surface or something like that, where we are seeing the energy in and energy out of the system adding to 0. Well, then we just sort of rearrange the equations here so that they were more easily solved using the kind of methods you learned in high school algebra. And if you actually pick this apart, you could make the model better and better. I mean, for example, if I change the transmissivity of each of these layers to, say, 50% for long-wave radiation, making little adjustments to the number, I get a temperature that's even closer to the right answer. So we messed around with the assumptions behind this and, changing the transmissivity of each of the layers. And the more we messed with it, the better and better an approximation to the real energy balance of the Earth, and the better the approximation to the real global mean temperature got. But, we were kind of just playing a game here. I mean, the atmosphere is not composed of just 2 layers. The whole idea of breaking the atmosphere up into layers is just a tool. We certainly aren't going to just sort of mess around with what we want the transmissivity of each of these layers to be until we get the right answer. Let's actually figure out how we could compute the transmissivity of each of these layers and so on. So, when we were doing this, we were forced to wonder, why were we limiting ourselves to just a small number of layers? Well, the answer is high school algebra. The more and more layers you add to this thing, the harder and harder it gets to solve. And these, like I'd have drawn there an n layer model. Yeah, good luck, if n is equal to, in a typical climate model, n might be 40 or something like that. Yeah, good luck solving a system of 40 equations and 40 unknowns anytime soon. And why are we making these gross assumptions about the transmissivity of the layer? It seems like we should be able to compute this. We shouldn't have to be making assumptions about this. It seems like we should be able to have information like how thick each of the layers is and how many absorbers there are in each cubic meter and so on, and actually compute the transmissivity of each of these layers. And of course we could. The adorably named Beer's Law from August Beer, it's actually correctly named the Lambert-Beer Law. I don't know who Lambert was, to be honest. But Beer's Law is the rule that is about how much radiation is transmitted through an attenuating medium. So this is what we really tackled on day 3 of the course, where we actually pulled out a numerical representation of Beer's Law. Notice that the left-hand side of this equation, as it's written here, is T lambda, which is the monochromatic transmissivity. It's the transmissivity of that layer of the atmosphere at that wavelength of radiation. It's a function of the wavelength. And it starts off just as the ratio of the amount of radiation that is transmitted through the layer to the amount of radiation that was incident upon the layer. Okay. It's complicated as to why we switched. There is a difference between I and E, if you're wondering why sometimes we have E's and sometimes we have I. Take physical meteorology. I'd love to explain the difference, but we aren't going to do that right now. But there's an amount of radiation that is transmitted through the layer to the amount of radiation that started off at the top of the layer, and we get this nifty equation and we can rearrange this and so on in lots of different ways. And, I liked the form that's circled here in this particular equation here, where the amount of radiation that's transmitted through a layer is a function of the amount of radiation that was incident upon the layer, delta S, B, and N. Now, each of those terms there, you're going to want to make sure you know what they are. What is delta S? What is B? And what is N? So that you can actually, you could in theory do the math. Now, in practice, we're not going to have calculators at the test or anything like that. But what are these things? And that in that exponential there, NB delta S, that's a thing. That's optical depth. NB delta S in this development is optical depth. And then e to the negative optical depth is going to be our transmissivity, right? Or we can multiply that by the amount of radiation that was incident at the beginning of the layer to find out how much radiation was transmitted by the layer, and so on. Optical depth is such a nice, handy property in any kind of climate science context here. Make sure you understand this concept. I know that folks were not thrilled with optical depth on the quizzes and so on that we saw. But you want to make sure that you understand how optical depth works. Like, what does it mean if the optical depth is 0? What does it mean if the optical depth is small, as in much less than 1? What does it mean if the optical depth is 1? What does it mean if the optical depth is big, like 10 or 20 or infinity or something like that? Know how these optical depths are related to the transmissivity of a layer, okay? There's a very direct relationship between optical depth and transmissivity. And you could see how you could apply this idea to our n-layer model of the atmosphere. As long as we knew for every one of these layers that we have broken the atmosphere up into, we knew what its thickness was, delta S, and we knew how many absorbers there were per cubic meter in that layer, and we knew how good they were, what was their effective attenuation cross-section, or whatever terminology we used in this class. We should be able to figure out the optical depth of each of these layers, from which we could then compute the transmissivity of each of these layers and so on. And we could do that based on things like observations. We could have observations of how much greenhouse gases are in each of these layers. And from the lab, we could find out things like what the attenuation cross-section of carbon dioxide molecules are, or oxygen, oxygen is not a greenhouse gas, water vapor molecules, or ozone molecules, or whatever. And we could actually solve for all of that. And we could make decisions about what that meant. I mean, for example, if I were thinking back to those slides about the atmospheric window, what is the optical depth of the atmospheric window for long wave radiation anyway? Well, in general, it's going to be very small. It's going to be bigger than 0, but it's not going to be as big as 1. Remember, if the e to the negative 1 would be, what, about 30% or something. If the optical depth is as big as 1, then only 30% of the radiation is transmitted through it. Well, we know by looking at this plot, nearly 100% of the long-wave radiation at these wavelengths is being transmitted through the atmosphere. If I had to guess, I don't know, optical depth in this range of wavelength is probably about 0.1 or something like that. In contrast, for example, at these wavelengths, in these bands, we can see that the optical depth in there is going to be bigger than 0, but not like infinite. I mean, it's going to be like 1 or something like that. And so you're going to have a transmissivity of somewhere around 30% or something like that. And gosh, if you start picking apart that, if optical depth is NB delta S, which of those terms is related to the concentration of greenhouse gases? Oh yeah, N. N is related to the concentration of greenhouse gases because N is how many of these absorbers there are per cubic meter. So if we increase N, the whole value of the optical depth goes up, and then e to the negative, to make it the transmissivity, could have a big effect. It's nonlinear and can have a very big effect. So we could pick all this through here. Now that we had built this idea about how changing greenhouse gases in the atmosphere, the physics of how that changes the profile of absorptivity in the atmosphere and transmissivity and so on, we were able to use that as a way to get our first insights into radiative forcing, or RF. And, the IPCC AR5 has a nice couple of paragraphs to help define radiative forcing and so on. How its units need to be watts per square meter because it's going to be the difference between energy. It's the change in the difference between energy in and energy out, where the energy in it's a flux, it's watts per square meter, and, all that kind of good stuff, all well explained in that part of the reading there. I like this definition. I thought I'd keep this slide in here. Again, these are all just screen captures from other slides. Where radiative forcing is an instantaneous value, it is the change in the net radiative flux, that's down minus up, due to an imposed change. Like I think we talked about, like if a volcano erupted. Okay, if a volcano erupts and puts a bunch of aerosols and gases and stuff into the atmosphere, there's a change in the difference between energy in and energy out. That change in the difference between energy in and out we'll see more mathematically in a couple slides. That's radiative forcing. It's how the radiative balance is imposing a requirement to have a temperature change. And in fact, that actual temperature change can be expressed as delta T, and is very much related to the radiative forcing by a parameter called lambda. Lambda is the climate sensitivity parameter. It is something that you get from models. It's not something you can derive, from theory or something like that. It has units of degrees Celsius per watt per square meter. And so for every watt per square meter, it's of change in the radiative forcing, it explains how many degrees Celsius of a temperature change is going to be needed in the climate. And we actually saw that, this is something you have to get from models. There's no way to just compute the climate sensitivity parameter. You have to actually get it from models where you run the model with some change in it, and from that you figure out what the temperature change was. And that, like for example, this histogram that we looked at in class that day was showing the output of a whole bunch of different models under scenarios in which they doubled the carbon dioxide from pre-industrial values. And you saw that it's a little bit uncomfortable. I mean, the mean climate sensitivity here in this case was about 3 degrees Celsius. And there were some that were less than 3 degrees Celsius of a temperature change, and there were some that were way more. But see, here's the deal. Very few showed temperature changes less than about 2 degrees Celsius. A temperature change of 2 degrees Celsius would be a nice outcome. And don't get me wrong, we would rather have no global warming, but if global warming is going to happen, we kind of need to keep it under 2 degrees Celsius. This model ensemble says that is not going to happen. There's very few models that showed that the climate sensitivity could be that small. On the other hand, a small number, but a real number of the models show that there was a climate change more than 8 degrees Celsius. That's a civilization ender, okay? We do not want the planet to be 10, 12 degrees Celsius warmer than it is now. Well, in that the outcomes here, this ensemble of model outcomes tells us that that's not terribly likely, but it's a whole lot it's a whole lot more likely than the relatively benign outcome of, say, 1.5 degrees Celsius. There should be all kinds of reasons why you see a diagram like this and you find it troubling. We then took that information and we went on day 4 and started actually kind of picking through, well, let's tell the story better. On that day, on day 4, we did 2 different things mainly. On that day, we mostly went over a quiz that didn't go all that well. Well, where do you think I'm going to get some of the questions for the test? I'm going to get some of them off of those old quizzes. So make sure you get that all straightened out as to what the right answer was and so on. And then we had a reading that day that folks weren't too nuts about. And so we kind of picked through and highlighted actual verbiage from the executive summary of Chapter 8 and actually kind of started using that as a way to frame up what we're doing with the rest of this module. And so, for example, we talked about the fact that based on the IPCC AR5 analysis, it is unequivocal that anthropogenic increases in the well-mixed greenhouse gases have substantially enhanced the greenhouse effect. Yeah, well, I don't think you found that anything of huge surprise. And we found out that, for example, aerosols partially offset the forcing due to well-mixed greenhouse gases and dominate the uncertainty in our total anthropogenic climate change. Later in the module, we're going to learn much more detail about what each of the different kinds of aerosols are, what is the sign of their radiative forcing, and so on. Here we were just sort of framing up, the executive summary paragraphs of Chapter 8 don't have a huge amount of detail. They're helping you understand what is the context, what does the stuff mean, and so on. We spent time learning about, for example, how ozone works as a greenhouse gas. Everybody, I think, is comfortable with how ozone works to protect the surface of the Earth from ultraviolet radiation, but ozone is also a surprisingly effective greenhouse gas, and there's 2 different places ozone can be. Down here in the troposphere with us, where it's purely a pollutant, there's almost no natural ozone near the surface of the Earth. And, well, it's a greenhouse gas, and we're putting it in the atmosphere, so that's a force that is driving towards warmer climate. There is ozone in the stratosphere, and we're depleting that. Well, that is a forcing towards climate, cooling. But as we found out in that particular lecture, the tropospheric part of that is 7 times bigger than the impact of what's going on in the stratosphere. And so ozone changes in the Earth's atmosphere are a net warming. We learned about changes in the albedo of the surface of the Earth, again setting the stage for some deeper understanding of them on day 6 of the course, but how changes in the surface of the Earth's albedo due to things like agriculture and urbanization and so on result in an a negative radius forcing. I mean, that's a cooling, but not a huge one compared to, say, greenhouse gases or something like that. Um, on that day, we also learned about changes in TSI, or total solar irradiance. And again, we'll see in the sixth day more detail about this, but I mean, there are changes that matter in total solar irradiance. Some of them are cyclical, like the 11-year sunspot cycle, but some of them are trends over the course of billions of years as the sun moves through its cycle as a main sequence star, through its life cycle as a main sequence star. But there's also long period on the order of centuries changes in solar output that are not necessarily all that well understood. And there are reasons to think that there has been a real increase in the total solar output since the Industrial Revolution. We're going to need to take that into account. We learned about natural ways in which there have been changes in the climate in the last 200 years or whatever, like volcanoes. I mean, volcanic eruptions put both gases and aerosols into the atmosphere. We did learn more about them on day 6. In many ways, day 4 and day 6 are tied together pretty nicely. Keep in mind, though, these volcanic eruptions is kind of a transient thing. I mean, the aerosols and so on that they add to the Earth's atmosphere, they have a lifetime from weeks to years, but eventually this a very transient climate event passes. We also spent some time that day talking about the role of water vapor. Um, Water vapor is a complicated story. It's a common objection that I get when I teach the 100 level classes, where students say, but wait a minute, water vapor has a much larger greenhouse impact than carbon dioxide, and we're not in control of water vapor. So why should we worry about the little bit of forcing due to carbon dioxide? It's an interesting question, but it's because the role of water vapor is to be a feedback in the climate system, not a forcing. Now, this might be terminology. I felt like people were a little glazed over that day. Water vapor is a greenhouse gas, but the concentration of water vapor in the atmosphere is controlled by the temperature. The temperature of the planet determines how much water vapor there is in the atmosphere. In contrast, like carbon dioxide is not controlled by the temperature of the water. The temperature of the planet. It controls the temperature of the planet. It isn't like a warmer world means more carbon dioxide emissions, at least not anthropogenic. It isn't that way. We don't drive more miles when it's warmer. We don't drive more miles when it's colder. The concentrations of anthropogenic greenhouse gases in the atmosphere don't depend on the temperature. They control the temperature. The concentrations of water vapor in the atmosphere amplify through a positive feedback the changes that are due to the greenhouse gases, but they are not controlling the temperature. They are the ones that are being controlled by the temperature. This actually put in place, by the way, the slightly complicated issue of stratospheric water vapor. Up in the stratosphere, there really shouldn't be much water vapor in a natural state, but methane that gets into the stratosphere can be oxidized by oxygen in the stratosphere in the presence of certain wavelengths of radiation and so on. And so anthropogenic increases in methane, which goodness knows there have been a lot of. I mean, we've more than doubled the amount of methane in the Earth's atmosphere. Well, that results in more oxidation of methane into water vapor in the stratosphere, and it's hard to get that out. Up in the stratosphere, there aren't rising motions that produce clouds and precipitation. The water vapor that gets into the stratosphere is a greenhouse gas, and it's really hard to get rid of. So we have this stratospheric water vapor that does provide a small but positive radiative forcing for the planet. If we move ahead to day 5 on the class, day 5 was the day after the big power outages and stuff like that, and we kind of just used that as a day to address some commonly asked questions about climate and climate change and physical climate and so on. That wasn't just a waste of your time. I want to make sure that you know the answers to these questions. It always gets a little bit awkward when there's certain questions that every atmospheric science major ought to be able to answer. Atmospheric science majors better be able to tell you things like, why is the sky blue? Why are clouds flat on the bottom and puffy on the top? Things like that. There's certain questions I think environmental science majors need to be able to answer. Things like, why can't we make more ozone? Or why can't we filter the carbon dioxide out? Or how do we know that it's humans that are causing the global warming and so on? And so some of those questions here we posed on that day. And they're all things that a lot of this stuff I was planning on talking about in the 4th module, but because we were all kind of having a bad day with the power outages and stuff, we did that day. So, like, for example, what was the story? Why couldn't we make more ozone? Well, it had to do with the fact that even though ozone generators exist, they don't actually produce that much oxygen. I'm sorry, that much ozone for the amount of power they consume, and it would be taking a huge chunk of the global energy production to produce enough ozone just to replace what we are depleting in the stratosphere. Um, why couldn't we just filter out the carbon dioxide? I mean, this could literally mean as in like some kind of apparatus that the air blows through and it extracts the carbon dioxide, or it could be like as in we grow dedicated forests that that remove carbon dioxide from the atmosphere by photosynthesis and then bury the wood that would then be, sequestering the carbon and so on. It seems like this should work, and we learned the problems as to why it wouldn't and so on. Um, no matter what, the scale is a problem. No matter what, we would have to be removing about the same amount of carbon from the atmosphere as we are putting in. So, we extract carbon from the lithosphere by the gigaton in the form of petroleum and coal and natural gas and so on. We would be, I mean, it would be an industrial scale process of how to remove carbon dioxide from the atmosphere. We would have a huge chunk of the surface of the earth would have to be dedicated to growing forests that would then be used to sequester the carbon by burying the wood and so on. It would be a very difficult process whatsoever. Storing the carbon would have a problem, but I think I have a later slide that shows that. Hey, what was this business about here? I heard that carbon dioxide is green. Doesn't carbon dioxide isn't it kind of like a fertilizer? Intro students love to tell me that it's not bad for carbon dioxide to be in the atmosphere because it's green. It's going to make the plants live better. Well, we actually analyzed the Earth's carbon cycle that day, and we found, yes, it does. And we, in fact, found out that the Earth's, the biosphere is uptaking more carbon dioxide and storing more carbon, and it's therefore doing us a favor in reducing or ameliorating global warming. But we learned about the fact that there's only so far we can push that, and it's only kind of a temporary solution, and it also makes ocean acidification worse, and all kinds of things that made that not such a great solution. But we're using clean coal, so that's not really a problem, right? All these problems are going to go away, right? Oh, well, we spent some time that day talking about the different technologies to produce clean coal, and what did it mean for coal to be clean, and what kind of emissions were we trying to reduce using clean coal, and what did that actually mean for carbon dioxide? I mean, was any of this a way to find a way to safely capture and store the carbon dioxide? Well, there were such technologies, but boy, they were dangerous. And what were you going to do if all this carbon dioxide got back out into the climate and so on? Review those slides to see all the pros and cons of these different strategies. I mean, just the business of sequestering carbon dioxide. Where are you going to store this stuff? Let's say you somehow could make some apparatus that stored the carbon dioxide that came off a coal-fired power plant or off of, out the tailpipe of a car. How does that help? You've now got a big tank full of carbon dioxide. How are you going to store it safely so that it doesn't get out? If it gets out, catastrophically, it's a suffocation hazard. If it leaks out, it's a global warming hazard. Where are you going to store this stuff in a way that it can be safely sequestered, on geologic time scales? Because we do not want this stuff getting back out. That day, we also talked about all these geoengineering type solutions. Like, well, couldn't we just make some kind of shade that like kept solar radiation from the sun from getting to the surface of the earth, kind of like a big umbrella in space? And we learned about like, you would need to, you had to launch one rocket a minute for the next 30 years or something to get enough material up into space up to the L1 Lagrange point to make this work. We learned about, like, for example, what about possibilities of geoengineering clouds, where by introducing more aerosols into cloud decks, we could make the albedo of the cloud deck higher and reflect more shortwave radiation for the surface of the Earth. And we learned the pros and cons of these things, all of which are good questions that a good atmospheric science or environmental science major should be able to answer. And then finally, we have this day 6, which kind of I intended as sort of a putting all the pieces together lecture. I'm not entirely sure it came off that way. I mean, we kind of went back and said, forget about all those arrows every which way on the energy balance. Let's just say we got an energy in and an energy out. And at first they're in balance, and then we do something that changes one of them. We increase the amount of energy in. Well, what will happen is the temperature of the Earth will adjust until the Earth is emitting more radiation by Stephen Boltzmann's law, and energy out will have changed. But that takes time. And the time that it took in order to restore that balance was determined by the thermal inertia of the Earth. I always hate to even use the word thermal inertia in class. Somebody who's taken a bunch of physics classes, somebody who's taken a bunch of atmospheric science classes, it's an ugly word. A physicist would never use it. They would say, well, let's talk more about its thermal conductivity. Let's talk more about its absorptivity. Let's talk more about its specific heat, things like that. Well, I don't want to get there. We all kind of understand this idea of thermal inertia. You put a cold turkey in a hot oven, it doesn't immediately become hot. It takes time for the cold turkey to warm up. And so, I mean, in the same way, we have a radiative flux at the surface of the Earth, and we are warming as not radiative flux, a radiative forcing at the surface of the Earth, and we are warming, trying to come back into a radiative balance. And we are not in a radiative balance right now. We had a net warming of about 0.6 to 0.9 watts per square meter, which is sort of our committed warming. We already have the greenhouse gases in the Earth's atmosphere that are causing that warming. There's nothing we can do about that. That is warming that is coming our way, and we've already put the gases up there. It's just a matter of taking the time for the Earth to actually warm up. This is the set of slides, by the way, where we got to a more mathematical definition of radiative forcing, where we actually saw that radiative forcing is this change in the difference between energy in and energy out, which you could then distribute the delta symbol there, and it's change in energy in minus change in energy out. And it has this important detail about how this is the change before the planet has made any adjustments to the change. Especially as you start talking about feedbacks and stuff like that, this terminology can be a little bit complicated. But it gave us a chance to kind of put some of these anthropogenic changes that we've been talking about into sort of a capstone about how they're all doing this in the context of physical climatology. And again, I'm not sure that was as clear that day as I wanted it to be, but like we could kind of summarize all these gases, which in the past we've had all these different scales. I mean, carbon dioxide's parts per million, methane's in parts per billion, ozone's in parts per trillion in the stratosphere. I mean, how are we comparing apples to apples here? And now we can put them all into the same units in terms of their radiative forcing, how many watts per square meter of radiative forcing there is associated with each of these gases. And we spent time on each of them and, why was stratospheric ozone and tropospheric ozone. You can see, by the way, look how the stratospheric ozone, the anthropogenic change results in a negative radiative forcing because there's less of a greenhouse gas. Hooray for us. Unfortunately, there's also more ozone, but that's another story. It's more ultraviolet radiation, but that's another story. And if you actually pick this all apart, what you saw is that while carbon dioxide is the most important of the greenhouse gases, actually all the other ones, if you added them together have about the same radiative forcing. That has implications for policy and so on. It gets really complicated for the public to sort this all out when they want to know about, global warming and stuff like that. Well, if you got to pick apart what's going on with methane and what's going on with stratospheric ozone and what's going on with the public, understandably gets very confused, and for that matter, lawmakers get really confused. We learned also about aerosols. We put aerosols into this context then of radiative forcing, and we said, well, there were different. Well, let's first of all make sure you do obviously need to know like definitions of aerosols. What are aerosols? What are the different pathways that these aerosols can get into the Earth's atmosphere? We kind of sorted the aerosols out into, I think it was 5 different piles, like mineral species and biological primary aerosol particles and inorganic aerosols and things like that. There were things like salt and so on. There's going to be all these different ways that we can do this. Some of them are natural, some of them are anthropogenic, and they are all important because they interact with both shortwave and longwave radiation. They could do it themselves by the direct radiative effect, the direct aerosol effect, or by the indirect aerosol effect, where the aerosols themselves are just making changes to clouds. I would certainly spend the time learning about sulfate. Sulfate aerosols come from the sulfur that's in fossil fuels. They don't have all that long of a life cycle in the troposphere. They're very easily washed out by precipitation. But if they get up in the stratosphere through like a volcanic eruption, they can be a very significant climate forcing. Make sure you know the sign of their radiative forcing in the climate and why it is that way. Make sure you know the same kind of questions about other aerosols like black carbon. Where does black carbon come from in the atmosphere? What is the sign of its radiative forcing? Does black carbon contribute to warming or cooling of the atmosphere? We spent a bunch of time on mineral dust. Remember, dust is different from sand. Sand particles don't really fly very far. They don't really have a radiative impact on the Earth's atmosphere. Dust, this very fine, finer than talcum powder dust that gets in the atmosphere in um, deserts. Also, anthropogenically from like poorly managed soils or from draining reservoirs or from construction sites and so on. Hey, what's the sign of the radiative forcing of mineral dust in the atmosphere? Does mineral dust act to cool the planet? Does it act to warm the planet? And then, well, once you talk about all those different aerosols, what is the net radiative effect of all of them? Well, it turns out the direct radiative effect from aerosols, what the aerosols themselves are doing, is a net radiative cooling, and not a terribly small radiative cooling. But there's also that indirect effect, which is how the aerosols are acting like cloud condensation nuclei and changing the distribution of drop sizes inside of a cloud. Instead of being relatively small numbers of big droplets, it's vastly more numbers of small droplets, and how that changes the properties of the cloud with respect to radiation, in particular its albedo for shortwave radiation. This is the aerosol indirect effect. I don't think I put a slide in here. Then both of them are negative. Both the direct and the negative, both the direct and the indirect effect are partially offsetting global warming. That's good, I guess, although they're a health hazard, and we are working actively to reduce things like particulate emissions and so on. So that's not good. We still have to sort all that out. I really like this particular slide. I really like this one that shows aerosol optical depth. It shows you, I like this idea of aerosol optical depth. It's the optical depth of a layer of the atmosphere due to the aerosols that are in it. I like the idea that, we can very concretely think about how many of these aerosols there are, how many absorbing bodies, and how effective each of them is, and how thick the layer that the dust or the pollution or whatever is in. I like the idea that it shows that this has to be a monochromatic quantity. You'll notice that it is the optical depth for radiation at a wavelength of 550 nanometers. I like it shows how we can see some very clear sources of aerosols, like Central Africa or West Africa or the Sahara or Saudi Arabia or East Asia and so on. I think this is a very helpful diagram to kind of put things all together. Switching away from aerosols, I like the whole story about how albedo has changed associated with the planet, becoming more industrial and more agricultural and more developed and so on. Notice it's a negative radiative forcing. We're actually making the albedo of the planet higher and reflecting more radiation. And it's not a huge effect, despite the fact we've spent about 200 years tearing down forests and grasslands and stuff like that. Makes us wonder about the reality of some kind of geoengineering solution to like increase the albedo of the Earth and prevent global warming. I also really liked this particular slide in which we could see how anthropogenic aerosols can also settle onto snowy surfaces and lower the albedo, and that also is a radiative forcing. Another important thing we did in that lecture was we kind of wrapped up by talking about changes in solar output. I got a diagram there of the 11-year sunspot cycle, and there is a real solar change. The amount of shortwave radiation reaching the surface of the Earth, there's about a difference of about 1 watt per square meter between the top and the bottom of that cycle. So there are times when we have a positive radiative flux and radiative forcing, and frankly not a small one. And there are times when we have a negative radiative forcing and frankly not a small one. But keep in mind, they kind of cancel each other out over a period of about 11 years. This in and of itself doesn't have a long-term climate consequence to it, but there are long-term climate consequences with regard to other things that can be happening inside of the solar environment. We need to know such things. And in fact, since the Industrial Revolution, there is good reason to think the sun has emitted more radiation, partly because at the beginning of the Industrial Revolution, we were coming out of the Maunder minimum, one of the grand solar minima. But anyway, so there we've got some ideas about solar, and we put it all together. And we said, oh my, if you add up all the radiative forcings since the Industrial Revolution, you see that our planet is experiencing a radiative forcing of about 1.6 watts per square meter. And at the present time, obviously depends on which observations you're using and so on. The book that I was getting this stuff from suggested a number of about 0.9 watts per square meter is our current way that we're out of balance. The NASA slide suggested more like 0.6. But either way, that means that the global warming that has already happened has kind of canceled out about somewhere around 0.7 watts per square meter of warming. Think of the turkey in the oven again. When we started out and put the cold turkey into the hot oven, there was a very large radiation imbalance. there was a great deal more energy going in from the oven into the turkey than coming out of the turkey into the oven. An hour into the baking process, the turkey is now much hotter, and there is a smaller energy imbalance, as now the turkey is emitting more radiation. But it has not yet achieved thermal equilibrium with the oven around it. And in the same way, the Earth has warmed partially and is already emitting more radiation than it did pre-industrial environment. Now we still are about halfway to go. We have a certain amount of committed warming just based on the greenhouse gases and the changes that we've aerosol changes and albedo changes and so on. And realistically, we have a lot of warming yet to go, and we'll keep adding greenhouse gases and keep moving the goalposts farther and farther into the future. All right, that's just a real quick overview. By the time you get this, there should also be a review sheet for you on Blue Line, and I hope that this information all helps, and please let me know if you have any questions.